In this video, we will talk about plotting 3D surfaces in MATLAB and Octave, three-dimensional surfaces. We are going to be looking at some commands in MATLAB, also in Octave, meshgrid, mesh, and surf. We would like to see what each of these is doing so that we can use them to create graphs that we want to create. So the first question we want to answer is, what does meshgrid do? This is the program we're going to analyze to get an idea of what the meshgrid function and the mesh function do. So this program, after this comment, starts with the command figure 1. We're going to create a figure, a graphics. We'll set x value equal to the integers from 1 through 6. Let's set the y values 2 through 7. These will be the values that we use on the x-axis and y-axis in our three-dimensional drawing of a surface. Then we'll execute this command. Capital X, capital Y equals meshgrid of the x values, comma, the y values. After this is executed, in the memory of the computer, we have a variable capital X, which is this two-dimensional matrix, and we have another array or matrix, capital Y, which has this contents. Both of these are two-dimensional. So let's see what happens here. We said that the x values were 1 through 6, the integers 1 through 6, and when this meshgrid command is executed, and the results of executing it are stored in the arrays x and y, this is what we get in x. The first row is 1, 2, 3, 4, 5, 6. The second row is the same, third row is the same, all the way down. All 4, or actually more than that, all 6 rows are the same. What about y? Well, the y values were 2 through 7. And so when this meshgrid command is executed, the two-dimensional array y has this form. The first column is 2 through 7. The second column is identical, so is the third, fourth, fifth, and sixth. So we get all of the columns being the same. Now, next thing that's executed is, after this meshgrid command, is z equals x squared minus y squared. Notice that we have a dot caret 2 here. This is an array. Dot and a caret is an array operation. We're going to square each element in this array x. We're also going to square each element in this array y, store them somewhere, subtract those two, and store the results in z. And it turns out that z will equal this two-dimensional array that we have down here. Now let's just check something while we're here. Let's look at this element. How about right here? Where did that minus 16 come from? Well, that minus 16 is in the fourth row, and it's in the third column. So if we look at the fourth row, third column of x, we have a 3. If we look at the fourth row, third column of this array y, we have a 5 in there. 3 squared minus 5 squared is 9 minus 25, and that's minus 16. All of the others are done similarly. For instance, if we look at, let's say, the first entry in the first row, first column, we have a 1 here. In y, in the first row, first column, we have a 2. And 1 squared minus 2 squared is minus 3, which we have down here in z. So we can see then that the elements of z, this array down here, are gotten by computing element-wise x squared minus y squared. The ijth element of z, the element in row I and column j, is computed by looking at the ijth element of x, squaring it, minus the ijth element of y and squaring it. So we're doing operations on these two matrices to get the values of z. Now what we want to do basically is to plot the values of z that we have here. They will form some sort of surface, or at least an approximation of the surface. And how is that going to be done? It will be done by using the mesh command, the mesh function, mesh x, y, and z. So x, y, and z are all two-dimensional arrays. And so let's see what happens when this mesh command is executed. When we execute the mesh statement, the program produces figure 1, which is shown here. And we can see that we have a surface over here of some sort, representing the equation that we had, which was z equals x squared minus y squared. If we want to, we can come up to here and choose rotate, and then we can rotate this graph around to see it from different perspectives. Suppose we take the first part of our program and we replace statement number 10 here. Instead of mesh xyz, we'll have surf xyz. The rest of the code up here is identical to what we had before. When the surf statement is executed, we will get this sort of depiction of the surface. Each of the little rectangular cells in this case is colored so that we can see this surface quite well. If we look at this, we notice that this is just an approximation of the surface x squared minus y squared, because the program that we had generated points x, y, z in the three-dimensional space and then basically drew a little rectangular patch there. So these patches kind of approximate the surface. But this is kind of a crude approximation, because what we have here are not that many rectangles actually. Can we do better? We could if we had a longer list of x values and y values here. So let's ask how we can do that. Let's look at the linspace command. Suppose I type y equals linspace 1, 6, 10, and let's execute that. It tells us that x is the following matrix. Columns 1 through 6, or 1 through 9, are these numbers. Column 10 has this one. It's a one-dimensional array with the first number being 1, the last number being 6, and they're equally spaced between 1 and 6. We could use a command like, let's say, x equals linspace. We can go from 1 maybe to 6 again, and we'll have 50 equally spaced points in the interval from 1 to 6, and there it is. At least part of it is. If we scroll down, we can see all the way down to the 50th element, which is 6. If we change our code for figure 1 to the following: first figure 1, then xvalues equals linspace from 1 to 6 by 20, yvalues equals linspace from 2 to 7 by 20, x, y, capital X, capital Y, equals meshgrid of the x values and y values, z is x squared minus y squared, and then surf x, y, z. We get this surface, and now if you count carefully, you'll find that there are, I guess, 20 rectangles going across this way and 20 rectangles going across this way for a total of 400 rectangles approximating that surface. We don't have to stop with 20, we could have 50 or 100, and MATLAB or Octave would still execute fast enough to give us a surface with even more accuracy. Suppose we look at an example for figure 2 where the uValues are 162534, the vValues are 273645, and uv equals meshgrid, uValues, vValues, w equals u square minus v square, mesh uvw. If you look at this carefully, you'll notice that if we look at the set of uValues, that's the same as the set of xvalues, but in this array we put them in a different order. They're not monotonically increasing. Similarly, the v-values here, the set of values 2 through 7 is the same as the set of values when we looked at x-values earlier. So you might think that the graph of this would be the same graph that we got before. However, if we look at figure 2, the figure created by this code ending with mesh uvw, it looks like this. We have some rectangles on top of other rectangles, perhaps on top of some other rectangles. It's garbled. The problem was these numbers in the uValues and vValues were not strictly increasing nor strictly decreasing, and the software in that case just didn't work properly. This was done in Octave. I suspect the same thing would happen in MATLAB, but I'm not sure. In summary, we saw that meshgrid takes two one-dimensional arrays as input and produces two two-dimensional arrays as output. We use these two-dimensional arrays to produce a third two-dimensional array by using a mathematical formula, for instance, x squared minus y squared for the surface that we want to plot, z equals x squared minus y squared. Mesh takes three two-dimensional arrays, the x array, the y array, and the z array, all two-dimensional, and produces a plot as its output. Instead of using the mesh command, we can use the surf command and get a surface which has some color to it and maybe easier on your eyes to see what's going on. Easier on your mind. Okay. Anyhow, there are more options we can use with mesh and surf. If you look into MATLAB documentation or Octave documentation, you can easily find out about that. Thank you for watching this video. Please stay tuned for more.